Hey, have you ever jumped rope? I think I have, but I can't be sure. Here's a rope, or here's how about we assume this to be a stretchy string slash spring that has a certain length, as you can see in the picture here. And when if you were to turn this thing into a jump rope, and especially if you can imagine it being a stretchy spring slash a stretchy string slash spring, you can imagine that this thing might, here's you over here. You're holding one end. Here's your cousin over here holding the other end, and you can imagine this stretchy spring string oscillating between looking something, oh boy, something like this. It's fine, and something like this, right? Of course you can. And here's your other cousin in the middle, jumping up and down, right? Sure. Now you may notice that this looks partly like part of some of the things we've been talking about. I mean, it's part of a wave, really. Really, it is, and really, there's a lot more happening than we're giving credit for. Really, what's happening is, well, you know how we've been talking about waves that can, or wave things like wave pulses that can travel on through media like this stretchy string spring thing, and reflection can happen, and reflection does happen when a wave encounters the boundary between one medium and another, and and if multiple wave pulses are sent, what happens is wave pulses that are incident in one direction, travel, propagate down this medium and reflect off that end there, and come back in the other direction and do this interference thing with the waves that are sent down, and so there's constantly all sorts of crazy propagation and reflection and interference that happens. And I don't know if you can tell, but I just keep pressing this pulse button over and over and over and over, and I'm doing it sort of randomly. And if I don't do it just right, boy oh boy, the result is a big huge jumbled mess, right? But if I do it just right, what you can do is, well, I guess jump rope. What you can do is create a wave that is made quite, because listen, if you're the person over here, if you here's cousin Bob, and here's cousin Jane over here, and Bob's, if Bob does some wiggling of this string rope, what really is happening, quite literally, what's happening is cousin Bob sending a stop. Oh no, cousin Bob is sending a pulse down that rope, and that pulse propagates this way. And if cousin Jane just sits there, really what happens is that wave reflects back this way, and it might undergo a phase shift and turn from a peak to a trough and all this stuff, and comes back and interferes, blah blah blah. And but as as you maybe know from experience in your long-lived life of jumping rope, you can't just, this doesn't work just any old way. You have to do this just right. There's one rhythm that this rope jumping will occur at. And what happens to be true about this is, what's happening is, you as a creator of oscillations, cousin Bob over here creates oscillations at a certain frequency, up and down and up and down and up and down and up and down and up and down, that happen to make this thing, quote unquote, work out just right. And what you create out of waves that are traveling this way and reflecting off of here and interfering with the waves that are coming back, maybe constructively, maybe destructively, over and over and over and over and over, what happens is you get this waveform that seems like all it's doing is sitting here, where this part moves up and down and up and down and stays in the same exact place, and these parts at the ends just never seem to move and never seem to move, even though, sure, yes, cousin Bob over here is actually moving his Bob, sure, hand up and down and up and down. But let's just sort of pretend that the hand's not moving up and down too much, or even if Bob stopped moving hand up and down, this thing could still keep going up and down until energy was dissipated and this oscillation stopped. But the short story, what I'm trying to get at here is if you create a situation just right where you send waves down this string and send them at just the right frequency. And I'm not gonna pretend that I can do it just right. But if you send them at just the right frequency, what you can get is a wave. What you can get is a wave that can look like this, where it seems like there's no motion of things like this. This peak seems to just turn into a trough and back into a peak, and this place just seems to go to here and back, and there's this whole symmetry thing that seems to happen, and we call this a standing wave. And so a standing wave is a wave that occurs because of lots and lots of stuff that's happening, because of lots of waves traveling one way and reflecting and traveling backwards and interfering, blah, 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 blah. Stuff we've talked about, but you can maybe imagine that you can get a rope that seems like it, or that looks like it just alternates between looking like that and later like this, and then back to the first, and then back like that. Yeah? Yeah? You've been there? We've all jumped rope? Sure, I suppose. Well, what you can also do perhaps is if you try a little differently, what you could do is if we change the frequency with which we drive this system or force this system, what you could do is instead of getting a case where we have a standing wave that looks like this, you might be able to get a standing wave that oscillates between looking, that's fine, isn't it? Nope, not good enough. Looks like this. Oh, much better. And at an instant later happens to, look like this. Yeah, maybe you can imagine that. And maybe you can imagine where if this one was sort of shoot, this one might be like more like yeah, right? Yeah. Okay. So, all right. Flashback. Sorry. When I was a child, when I was a young boy, we had things in our homes called telephones, and they were bolted to the wall. And the telephone, if you were, as telephones got a little more fancy, what they would have is a really long cord, and the cord looked like this, a nice big rubbery coated wire that was a spring. And what you could do is if you wanted to, go in the other room to talk, you just walk away with the phone and it would turn into a big spring like this, a big long spring. And I would do this as I was talking to people on the telephone, like an old-timey weirdo. And what I would do is I would do this with my phone cord. I would find just the right frequency with which I could force this end up and down, and I would make it do stuff like this. And I would create standing waves, not knowing that what I was actually doing was blah, 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 sending wave pulses down the spring and having them reflect off of the end and having them come back and reflect over and over in ways that were sometimes constructive and sometimes destructive. Yeah, I was doing that. Oh, the glory days of talking on the telephone. So, let's get into the details. Here's what's really happening. I got a great thanks to the gorgeous people at Wikipedia. Look at this. Here's how a standing wave is created. So look at this green wave propagating to your right at a very constant frequency. We can tell this as a very constant frequency because there's a very constant wavelength, yes, and this wave moves at a very constant speed, so it must have a very constant wavelength. And imagine this wave moving to the left, propagating to the left. Imagine that being a wave that is reflected off of a boundary over here. And what you can see, can I pause? I'm not sure I can pause. Maybe I can zoom. Oh boy, I can't pause. But if I were, what you can imagine is look at any instant. At any instant, sometimes green peaks line up with green peaks, and we get a big peak. Sometimes green troughs and green troughs make a big trough. Sometimes a green trough and a blue peak make a totally destructive interference. So this is how standing waves are made. Waves that are moving at the same frequency in opposite directions because one might have been reflected off of this end. What they do is interfere with each other in ways that are alternatingly constructive and destructive. And this red wave is quite literally the mathematical sum of the two amplitudes of those two waves that are interfering. And sometimes you get big, and sometimes you get big, and sometimes you get nothing, and big, and nothing, and big, and destructive and constructive. That's what a standing wave is. And all the while, you thought you were just jumping rope. Okay, so let's get a little more into the analysis of it all. So what there are many ways, or for a certain length of a string, let's call it a length L. There are several, really an infinite theoretical number of frequencies at which you can create a standing wave, right? And the lowest frequency, which means, so look, the smallest, I apologize, the smallest frequency slash the lowest frequency, which translates to, now this is a single medium in a uniform medium, so that means there's a wave that travels at a constant speed along here. So a small frequency means the largest wavelength. I apologize for the sloppiness of the writing. And what I'm saying here, how I'm relating these is I'm saying that I'm using a wave equation, V equals F lambda, and if there's a constant wave speed on this string, well, sure, a small frequency means a big wavelength. Well, the biggest possible wavelength that you could create a standing wave on a string looks like this. And here's the reason. On a string, when we make a standing wave on a string, what we assume is that the ends of the string are physically held down and not allowed to oscillate. I happen to have a thing near me that creates standing waves on strings where the ends of the string are physically held down, and what I can do is I can, from the center of this thing, create wave pulses that quite literally propagate in each direction, and reflect off the ends and come back and interfere with each other. And that system is my my beautiful, what model is this thing? Who cares? It's this lovely guitar I have. Listen. Oh, wow. So what's happening is I have just done a little pluck in the middle of this string, and I've created a place where lots of oscillation happens. And of course, I hope you can recognize that on a guitar string, the ends of the string are physically held down, not allowed to oscillate. And so when reflection happens at those ends, it's of a certain variety where, sure, maybe a phase shift happens where as a peak approaches this end, it comes back as a trough. And who cares, I guess, and a peak that approaches this end reflects and comes back as a trough. And those peaks and troughs are interfering and at just the right frequency such that we get, you can imagine watching a guitar string, maybe if you looked real close, oscillate like this, yes? Right? Where, well, maybe you can, maybe it makes sense to you that, well, wow, what I'm seeing here is half of a wave, where the other half of the wave, if we were to have a string long enough, don't mind this string over here, would look like that. And what we could say is we could start to make some basic relationships between, well, this string length is a half of a wavelength, and or the wavelength for this oscillation would be, if we could extend the string, would be twice as long as the string. Yeah? Well, as we sort of talked about. I remember with my old timey phone cord, you can also do this, right? Because here's the deal: for a string, as long as you have this or meet this criteria where the ends of a string are held down, what we could get is you could, instead of forcing the string up and down and up and down and up and down and getting one standing wave pattern, you might go up and down and up and down and up and down and up and down, and you might get what looks like it. I mean, physically looks like a different pattern. And what might happen, I'll just draw it again, but we would get something that looks like this, where this standing wave could oscillate between looking, I can do it better, between looking like, looking like this. Ugh, I know I'm so picky. Looking like this, fine, and looking like this at some instant later in time. Yeah? And here we could say, well, this length, L of this string, happens to, well, capture two half wavelengths. I know, why wouldn't you just say lambda, but you'll see in a minute. Or this wavelength is 2 L over 2. I know, why wouldn't you just say L? You'll see in a minute. 2 L over 2. So these, and maybe you can imagine that there's lots of different ways we could make this happen. And by what I mean this is where we have this standing waveform, which the standing wave create, which looks, again, it looks like, notice how this peak turns into a trough, and this peak, do you see my little cursor, turns into a trough, and it looks like nothing's moving, right? But what really is happening is, look at the blue wave, it's created by a wave that's propagating to the left. Look at the green wave, and a wave propagating to the right, interfering constantly, sometimes right now constructively, and then destructively, and then constructively, and then destructively. And so there's so much happening, but what you end up seeing is a wave that looks like it doesn't go anywhere. It doesn't go anywhere. It looks like it's just standing there, and we call those standing waves. All right, and again, I wish I could pause. How do I pause? I don't know much. Ready? So, oh wait, ready? This is homework. Maybe watch. Ready? So if oh yeah, good. Oh wait, that's fine. See, look, no. Ready? Go. Fine. Right. So right now, see this? See the red wave that's the interference result of the green and the blue? I mean, that happens to have, look, like sort of a place at the end that doesn't seem to be, that's like kind of right along the equilibrium line, right? And notice how these, like at the ends, have places right along the equilibrium line. There is a certain criteria. There is a criteria for standing waves on strings, that what has to happen at the end is these ends are physically held down and they're not allowed to oscillate. And we call these places nodes. We call each one of these things a node. Node. This is a node. Well, let's do this. We'll say X node. And here's a 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 node. And those nodes are places where the only thing that ever happens, here's a node. Well, how about this one? Here's a node here. The only thing that ever happens at a node is the green and the blue wave interfere destructively. Those places never do any oscillation at all. And then you have these places. Can I just, does that work for you? Yeah. These are called antinodes. And that's a place like this, and like this, and like this. And I'm not saying that, and so here basically is an antinode. This is the location of an antinode. It's not that this is one and that's one. That's a location of, those are locations of antinodes, where at those locations, here, if you look at the green and the blue wave at any instant, they're always what I would call in phase, right? Right now they're both peaks, and right now they're both troughs, and right now they're both peaks. And any time and any instant where you look at what's happening right here with green wave and blue wave, they're always doing the exact same thing. Yeah, they're always interfering constructively. That's what happens at what we call antinodes. So nodes, this is where always destructive interference happens. Antinodes, this is where always constructive interference happens. Guess fine? Well, guess what? There are lots of ways, I mean, theoretically, infinite number of ways where we could meet this criteria where at the end of a string, we have to have, well, quite literally, the string physically held down. And so, this one, so we have to have a node at this end, oh boy, a node at this end, and a node at this end. And you have to be able to fit part of a wave on a string such that you can have nodes at each end. Well, it could work also if, nope, it could work also if you had a standing wave that looked like this. It's fine, you get it, where it oscillates between looking like the solid and looking like the dashed. Where guess what? If we relate the length of this string L to wavelength, well, can you tell that there are now 3 halves of a wavelength? Or that the wavelength is 2 lambda over 3? Did I do the algebra right? Nope, I didn't. 2L over 3. Yeah? And imagine we could keep going and we could create a situation where, let's see, we could have, again, we need, our criteria for a standing wave in a string is we need nodes on each end. And what we could do is something like this, where we get a wave that oscillates between looking like this and looking like this. Oopsies. Fine. And can you recognize that this length L from here to here now captures 4 half wavelengths? Or that lambda is 2, let's see, 2L over 4. What do I do over here? Yeah, 2L over 3, sure. Right, and so on and so on. So the deal is, if we need a standing wave to be formed on a string, what we need is a node on each end, and that means that as long as we can capture 1 half of, or an integer number of half waves, then we can quote, make it happen. All right, now check this out. If we make the connection between wavelength and frequency and wave speed, now notice, here's what we said. We said, well, this length is half a wavelength. Therefore, the wavelength is twice the length of the string. Now, we could say there's this equation that relates things like, we could say this, right? V is F lambda. Really, it's that the wavelength of a wave depends on these two things. But check this out. What frequency will this oscillate at? Well, we can say that's V over lambda, or in this case, there's some speed that the wave travels at, and then the wavelength is 2L. Yeah? And I'm going to call this F naught. I'm going to call this the fundamental frequency. It's the lowest frequency that a string will vibrate at. I'm plucking it right in the middle. And the middle of the string is going rah, 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 oscillating back and forth and back and forth. Yeah? And there's some frequency that, that we hear a frequency. We hear the frequency of that oscillation as the pitch of this sound. Now, there's a long story about what you're actually hearing. You're actually not hearing like the string vibrate, but let's just put that aside for now. All right, now here, what we have is, okay, we have a different wavelength. Here, the wavelength was twice as long as this string. Here, the wavelength is, well, quote unquote, simply the length of the string. So there's a frequency. If we say that this, again, V is F lambda, we can say there's a frequency for this one that's V over this lambda. Well, that's V over lambda is 2. Watch, it's 2L over 2. That's why I wrote it like this. Lambda is 2L. Watch, it's actually 2L divided by 2, but divided by means multiplied by. Yeah? Whoops. 2 of these. Notice. V over 2L. V over 2L. And now we have 2 of those. So hopefully it makes sense to you that, look, what we have is a string which is a certain medium where the wave speed on this medium is constant. And what we have is this thing vibrates or oscillates with a certain, or at a certain, or there's an oscillation of a certain wavelength. This wavelength is half as big. And so what that means is if wavelength is half as big, then frequency must be twice as big, and that's why this 2's there. So look, this frequency that I'm going to call F2 is 2 F0. This stuff is F0. And this frequency is twice the fundamental frequency. Well, guess what this one is? This frequency, let's start here. Let's start again with our basic wave equation. V is F lambda. Okay, so the frequency is V over lambda. All right, so the frequency is V over 2L divided by 3. So this frequency, I'll call it F3, is 3 F0. Because again, this is our same F0. Our same fundamental frequency, V over 2L. And guess what this one is? This V is, this F, what I'm going to call F4, is 4 F0. And so on, and so on, and so on. Yes, fair? Now, oh boy, hello. Look at this. So now this, I don't know who's this, I don't know. So lovely, mother of pearl here, love. So yeah, so musically, right? Here's how some of this works, right? When I do this, what I'm doing is plucking the low E string here. It kind of doesn't matter where, but what I'm doing is plucking it in the middle, such that I'm plucking it, here, such that this thing goes wow, exaggerated, between that and this. Way exaggerated, right? And the middle of the string oscillates up and down and up and down. And there's this anti-node in the middle and a node at the end and a node at the end. Yeah? And this big wavelength corresponds to small frequency because because wave speed is constant, right? So here's what we can do though. I can make this happen. Now what I can do is, one thing I can do is I can change, here, let's just write this. We can say that F is V over 2L. F naught is V over 2L. So I can make a frequency that depends on what's the speed of the wave, and this depends on the tension on the string, which you guys have heard me say, and it depends on the length of the vibrating string, right? So if that length of the vibrating string is this whole length, then we get this. But if that length of the vibrating string is, say, this, but what's this, 3, 5, 7th fret. If the length of the vibrating string is this, and now we get a wave that has a shorter wavelength, what we'll get is a higher frequency. Here's 7th fret, listen. Here's the whole darn string. But if I put my finger here and fret and hold the string down against that metal thing called a fret, what we get is this. Whoops, and we get this. That doesn't sound great, does it? We get the start. Oh, that was actually the 9th fret. So notice what I did was make the length shorter. That makes the frequency bigger, and we go. And so frequency, so here's lowest frequency, here's higher frequency. Yeah, here's higher frequency. Yes? So what we need to, or one thing that's nice to recognize if you have any care in your brain about music, is that higher frequency means higher pitch. Okay, all well and good. Now let's imagine this. One thing I can do is here's our fundamental frequency. What I can do is I can make this happen in one of a couple of ways. One thing is I could simply do this part, which means just make half of the original string length vibrate. Yeah? And what that means is, it quite literally means, if I just want to make, where is it? There it is. If I just want to make, let's see if we can figure out this scale here. And I mean like the spatial scale. If I just want to make half of this string vibrate, where's the middle? Where's the middle? Well, guess what? The middle is right there. I promise you it's right there. Right? I mean, you can maybe tell spatially, but I promise you it's right there. This happens to be called this happens to be the 12th of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12th fret. Knew it. And the 12th fret on a guitar happens to be exactly halfway down the guitar. So if I put my finger here and hold that bar down, or hold what I really do is put my finger like in this place, which holds the string down along this metal bar, what we get is now we're going to have only half of the original string vibrating. And so here's the whole string, but if I only make half the string vibrate, here's what we get. Here's the whole string, here's half the string. And so hopefully if you have any musical inclination, what you may be able to tell is here's what we did. We went from a certain frequency, F0, to a different frequency that is twice that. And when we double frequency, here's tonally, musically, what we hear. Fundamental. Here's the next one. Some of you may recognize that as an octave difference. So if you double a frequency, we in Western music culture stuff recognize that as an octave. Now, there's a different way that I can make this happen. One way is to only let this part of the string oscillate. The other way is to do this and to make the whole string oscillate, but just don't let the middle oscillate. And the way that I do that is I use my finger sort of gently, and I don't push, I don't push the string all the way down onto this 12th fret. What I do is literally, instead of mashing my finger here, which makes this string contact that metal fret there, what I do is I put my finger lightly, just lightly there. And don't push it down, but I just hold it a little bit. And when I pluck here, what happens is my little light touch of the finger doesn't let this place oscillate. But then what does happen, what I've done is created a node at that location, and then the whole, oh boy, and then the whole darn string will oscillate, And what we get is, well, the same double frequency that you heard before. So watch, I'll do it very carefully. Oh boy, I got it. So here's fundamental. Oh, no, fundamental. And then I'm going to very lightly touch right here. It's hard to do with. Very lightly touch right there, but then I'm going to release it as soon as I pluck right here. Listen, ready? Here's fundamental. And then I just touch very lightly. Oh, there it is. And I wish I could show you, but I have no hands on the guitar. And what you hear, listen, here's when I actually fret the 12th fret. Sure, one octave up. Here's when I just make a note there. Oops, sorry, gosh. There it is. Here's fret. Here's just make just make the node right there. And then guess what? I can make this happen by lightly putting my finger a third of the way down the guitar string, a third of the way down the guitar string. Let's see. Where's a third of the way down? Boy, let's see. A third of the way looks like thirds, maybe like. Yeah, it's pretty close. Yep, a third of the way happens to be right there on this 7th fret, right? 1, 2, 3, 4, 5, 6. Nope, 7. The 7th fret. The 7th fret in the guitar happens to be exactly a third of the way down. So here's what that sounds like. All right, so here's fundamental. Here's 12th fret right here, octave up, and here's 7th fret. Hear that? Here's fundamental. Here's 12th fret. Here's 7th fret. So I just did this, just touched lightly right there, and I went from fundamental here to this next one that we actually call the, we call the second harmonic. To next we went to the third harmonic. And it sounds different. And notice from the fundamental to the second harmonic, we doubled the frequency. Whoops. And we went up by an octave. But notice when we go from second to third, we don't double that. So we don't go up another octave. But guess what? If we go from the second harmonic to the fourth harmonic, we do double the frequency. And I can do that by putting my finger on the 5th fret. So listen, fundamental, second harmonic, fourth harmonic. There it is, fourth harmonic. Yeah, we've gone up an octave again. Beautiful, right? Neat, right? All right, well, there's a lot there. Some music theory, a lot of physics. What you need to recognize is that for a standing wave to exist on a string, there are certain criteria that must be met, and namely that's that there must be a node at each end of the string. And as for that to happen, what that means is the string must capture some integer number of half wavelengths. And then what you can do is say, well, I can relate the length of that string to the wavelength of the wave, and I can use the general truth that, that a wave's speed and its frequency and its wavelength are related. And then you can, relate what you have to relate. And then you can say things like, well, there are lots of different ways for standing waves to exist on a string. And what happens is there happens to be this not coincidence, but that's why they're named, like a second harmonic, like a harmonic for a wave on a string. The harmonic number is like the multiplier of the fundamental frequency. So the second harmonic is double the frequency of the fundamental. The third harmonic is triple the frequency of the fundamental frequency. The fourth harmonic is quadruple the frequency of the fundamental frequency. Okay? A lot there, buddies. but the basics, lie in some truths about what has to be true for a wave on a string. Nodes at the end. All right, buddies. Thanks.